Edison, His Life and Inventions, by Frank Lewis Dyer and Thomas Commerford Martin. Appendix 18. Edison's New Storage Battery. Generically considered, a battery is a device which generates electric current. There are two distinct species of battery, one being known as primary and the other as storage. Although the latter is sometimes referred to as a secondary battery or accumulator, every type of each of these two species is essentially alike in its general makeup. That is to say, every cell or battery of any kind contains at least two elements of different nature, immersed in a more or less liquid electrolyte of chemical character. On closing the circuit of a primary battery, an electric current is generated by reason of the chemical action which is set up between the electrolyte and the elements. This involves a gradual consumption of one of the elements and a corresponding exhaustion of the active properties of the electrolyte. By reason of this, both the element and the electrolyte that have been used up must be renewed from time to time, in order to obtain a continued supply of electric current. The storage battery also generates electrical current through chemical action, but without involving the constant repriming with active materials to replace those consumed and exhausted as above mentioned. The term storage, as applied to this species of battery, is however a misnomer, and has been the cause of much misunderstanding to non-technical persons. To the lay mind, a storage battery presents itself in the aspect of a device in which electric energy is stored, just as compressed air is stored or accumulated in a tank. This view, however, is not in accordance with facts. It is exactly like the primary battery in the fundamental circumstance that its ability for generating electric current depends upon chemical action. In strict terminology, it is a reversible battery, as will be quite obvious if we glance briefly at its philosophy. When a storage battery is charged, by having an electric current pass through it, the electric energy provides a chemical effect, adding oxygen to the positive plate and taking oxygen away from the negative plate. Thus the positive plate becomes oxidized and the negative plate reduced. After the charging operation is concluded, the battery is ready for use, and upon its circuit being closed through a translating device, such as a lamp or motor, a reversion discharge takes place, the positive plate giving up its oxygen and the negative plate being oxidized. These chemical reactions result in the generation of an electric current as in a primary battery. As a matter of fact, the chemical actions and reactions in a storage battery are much more complex, but the above will serve to afford the lay reader a rather simple idea of the general result arrived at through the chemical activity referred to. The storage battery, as a commercial article, was introduced into the market in the year 1881. At that time, and all through the succeeding years, until about 1905, there was only one type that was recognized as commercially practicable, namely that known as the lead sulfuric acid cell, consisting of lead plates immersed in an electrolyte of dilute sulfuric acid. In the year last named, Edison first brought out his new form of nickel iron cell with alkaline electrolyte, as we have related in the preceding narrative. Early in the 80s, at Menlo Park, he had given much thought to the lead type of storage battery, and during the course of 3 years had made a prodigious number of experiments in the direction of improving it, probably performing more experiments in that time than the aggregate of those of all other investigators. Even in those early days he arrived at the conclusion that the lead sulfuric acid combination was intrinsically wrong, and did not embrace the elements of a permanent commercial device. He did not at that time, however, engage in a serious search for another form of storage battery, being tremendously occupied with his lighting system and other matters. It may here be noted, for the information of the lay reader, that the lead-acid type of storage battery consists of 2 or more lead plates immersed in dilute sulfuric acid and contained in a receptacle of glass, hard rubber, or other special material not acted upon by acid. The plates are prepared and formed in various ways, and the chemical actions are similar to those above stated, the positive plate being oxidized and the negative reduced during charge and reversed during discharge. This type of cell, however, has many serious disadvantages inherent to its very nature. We will name a few of them briefly. Constant dropping of fine particles of active material often causes short-circuiting of the plates, and always necessitates occasional washing out of cells. Deterioration through sulfation if discharge is continued too far, or if recharging is not commenced quickly enough. Destruction of adjacent metalwork by the corrosive fumes given out during charge and discharge. The tendency of lead plates to buckle under certain conditions. The limitation to the use of glass, hard rubber, or similar containers on account of the action of the acid, and the immense weight for electrical capacity. The tremendously complex nature of the chemical reactions which take place in the lead-acid storage battery also renders it an easy prey to many troublesome diseases. In the year 1900, when Edison undertook to invent a storage battery, he declared it should be a new type into which neither sulfuric nor any other acid should enter. He said that the intimate and continued companionship of an acid and a metal was unnatural, and incompatible with the idea of durability and simplicity. He furthermore stated that lead was an unmechanical metal for a battery, being heavy and lacking stability and elasticity, and that as most metals were unaffected by alkaline solutions, he was going to experiment in that direction. The soundness of his reasoning is amply justified by the perfection of results obtained in the new type of storage battery bearing his name, and now to be described. The essential technical details of this battery are fully described in an article written by one of Edison's laboratory staff, Walter E. Holland, who for many years has been closely identified with the inventor's work on this cell. The article was published in the Electrical World, New York, April 28, 1910, and the following extracts therefrom will afford an intelligent comprehension of this invention. The A-type Edison cell is the outcome of 9 years of costly experimentation and persistent toil on the part of its inventor and his associates. The Edison invention involves the use of an entirely new voltaic combination in an alkaline electrolyte, in place of the lead peroxide combination and acid electrolyte characteristic of all other commercial storage batteries. Experience has proven that this not only secures durability and greater output per unit weight of battery, but in addition there is eliminated a long list of troubles and diseases inherent in the lead-acid combination. The principle on which the action of this new battery is based is the oxidation and reduction of metals in an electrolyte which does not combine with, and will not dissolve, either the metals or their oxides, and an electrolyte, furthermore, which, although decomposed by the action of the battery, is immediately reformed in equal quantity, and therefore in effect is a constant element, not changing in density or in conductivity. A battery embodying this basic principle will have features of great value where lightness and durability are desired. For instance, the electrolyte, being a constant factor as explained, is not required in any fixed and large amount, as is the case with sulfuric acid in the lead battery. Thus the cell may be designed with minimum distancing of plates and with the greatest economy of space that is consistent with safe insulation and good mechanical design. Again, the active materials of the electrodes being insoluble in, and absolutely unaffected by, the electrolyte, are not liable to any sort of chemical deterioration by action of the electrolyte, no matter how long continued. The electrolyte of the Edison battery is a 21% solution of potassium hydrate, having, in addition, a small amount of lithium hydrate. The active metals of the electrodes, which will oxidize and reduce in this electrolyte without dissolution or chemical deterioration, are nickel and iron. These active elements are not put in plates as metals, but one, nickel, in the form of a hydrate, and the other, iron, as an oxide. The containing cases of both kinds of active material, Fig. 1, and their supporting grids, Fig. 2, as well as the bolts, washers, and nuts used in assembling, Fig. 3, and even the retaining can and its cover, Fig. 4, are all made of nickel-plated steel, a material in which lightness, durability, and mechanical strength are most happily combined, and a material beyond suspicion as to corrosion in an alkaline electrolyte. An essential part of Edison's discovery of active materials for an alkaline storage battery was the preparation of these materials. Metallic powder of iron and nickel, or even oxides of these metals, prepared in the ordinary way, are not chemically active in a sufficient degree to work in a battery. It is only when specially prepared iron oxide of exceeding fineness, and nickel hydrate conforming to certain physical as well as chemical standards can be made that the alkaline battery is practicable. Needless to say, the working out of the conditions and processes of manufacture of the materials has involved great ingenuity and endless experiments. The article then treats of Edison's investigations into means for supporting and making electrical connection with the active materials, showing some of the difficulties encountered and the various discoveries made in developing the perfected cell, after which the writer continues his description of the A-type cell as follows. It will be seen at once that the construction of the two kinds of plate is radically different. The negative or iron plate, Fig. 5, has the familiar flat pocket construction. Each negative contains 24 pockets, a pocket being 1/2 inch wide by 3 inches long, and having a maximum thickness of a little more than 1/8 inch. The positive or nickel plate, Fig. 6, is seen to consist of 2 rows of round rods or pencils, 30 in number, held in a vertical position by a steel support frame. The pencils have flat flanges at the ends, formed by closing the metal case, by which they are supported and electrical connection is made. The frame is slit at the inner horizontal edges, and then folded in such a way as to make individual clamping jaws for each end flange. The clamping in is done at great pressure, and the resultant plate has great rigidity and strength. The perforated tubes into which the nickel active material is loaded are made of nickel-plated steel of high quality. They are put together with a double-lapped spiral seam to give expansion-resisting qualities, and as an additional precaution small metal rings are slipped on the outside. Each tube is 1/4 inch in diameter by 4 1/8 inches long, and has 8 of the reinforcing rings. It will be seen that the A positive plate has been given the theoretically best design to prevent expansion and overcome trouble from that cause. Actual tests, long continued under very severe conditions, have shown that the construction is right and fulfills the most sanguine expectations. Mr. Holland in his article then goes on to describe the development of the nickel flakes as the conducting factor in the positive element, but as this has already been described in Chapter 22, we shall pass on to a later point, where he says, "An idea of the conditions inside a loaded tube can best be had by microscopic examination. Fig. 7 shows a magnified section of a regularly loaded tube which has been sawed lengthwise. The vertical bounding walls are edges of the perforated metal containing tube. The dark horizontal lines are layers of nickel flake, while the light-colored thicker layers represent the nickel hydrate. It should be noted that the layers of flake nickel extend practically unbroken across the tube and make contact with the metal wall at both sides. These metal layers conduct current to or from the active nickel hydrate in all parts of the tube very efficiently. There are about 350 layers of each kind of material in a 4 1/8 inch tube, each layer of nickel hydrate being about 0.01 inch thick, so it will be seen that the current does not have to penetrate very far into the nickel hydrate, 1/2 a layer's thickness being the maximum distance. The perforations of the containing tube, through which the electrolyte reaches the active material, are also shown in Fig. 7. In conclusion, the article enumerates the chief characteristics of the Edison storage battery which fit it preeminently for transportation service, as follows. 1. No loss of active material, hence no sediment short circuits. 2. No jar breakage. 3. Possibility of quick disconnection or replacement of any cell without employment of skilled labor. 4. Impossibility of buckling and harmlessness of a dead short circuit. 5. Simplicity of care required. 6. Durability of materials and construction. 7. Impossibility of sulfation. 8. Entire absence of corrosive fumes. 9. Commercial advantages of light weight. 10. Duration on account of its dependability. And 11. Its high practical efficiency. End of Appendix 18.